Welcome to the Chemistry of Life. This is a bio presentation for Science 9. This is Chapter 2, Section 2 of the bio textbook, but you have, of course, a reading packet called Reading Packet 2 or Reading 2, which is essentially the chapter. There may have been some pages omitted that were just charts or something, but you have the chapter. Otherwise, this is part 3 of a 4-part presentation, I believe. There may be 5 parts, depending on how the last section goes. If it's too long, I'll break it up into 2 parts. Otherwise, part 3 and maybe just part 4. So, with this presentation, what we want to look at is we want to look at some specifics of water, because water is essential to life as we know it on planet Earth. It will be certainly very interesting if life on other planets, on other moons maybe, if it's water-based or if it's something else, when eventually we do find life. And I personally believe, in my own opinion, that we will eventually find life, whether it's in 50 years or 150,000 years. Eventually, I think there is other life out there in the universe, and we will discover it. Of course, we're doing the student learning map. The student learning map here is your second question, the properties of water. What are the properties of water that support life? Remember, with this narrated presentation, or if it's saved as a video, you can always pause, stay on the slide long enough to fill out your guided notes or your student learning map, and then hit play and keep on going. With the presentation, you can also mute the volume. You know, if you do not need to hear any of the explanations, or if it's your second time through, just mute the volume. Otherwise, here we go. Okay, the water molecule. And I do have a pen activated so I can interact with this. Okay, so water molecules. Water as a single molecule is neutrally charged because it is covalently bonded. And in fact, whether it's ionically or covalently bonded, any compound eventually is just neutral. It's the most stable arrangement for a compound. But how it arrives at being neutral is going to be different for one versus the other. With covalent substances, it's just the sharing of electrons, so there are no actual charges involved. The compound will always be neutrally charged. However, in water's case, like many compounds actually, there is an unequal sharing of electrons, which is what a covalent bond is. It's a sharing of electrons. However, those electrons do not have to be shared equally, as we talked about in the the presentation prior to this, where electrons can be shared equally and they can be shared unequally, and that has consequences. When they're shared unequally, this creates a molecule that has charged ends. And I have a diagram right up top here. And that in that diagram, let me change my color so it stands out a little bit. So on the oxygen side, oxygen is a very strong attractor for electrons. And so as it shares electrons with hydrogen, it attracts these electrons. And it attracts them more strongly than the hydrogen does. So the electrons orbit the oxygen much, much longer, many more times than when it zings out and orbits the hydrogen once and zings back. Or in this case, this hydrogen orbits, and then zings back. In this case, the electrons spend most of their time around the oxygen atom. So what this does is this creates a partially negative area on the side of the oxygen. On either side of the hydrogens you see up here at the very top, they have a slightly positive charge. Now these are not true ionic charges, which are the true charges if we're going to talk about that, but these are just partial charges, and they typically show it with a Greek symbol, kind of like an unusual, it looks honestly to me like kind of like a fancy Christmas ornament or something, or some kind of weird S. But in any case, it's a lowercase Greek letter. I think it's the lowercase Greek delta. But in either case, though, it's just on the hydrogen side, there's a partially positive charge on either end. Normally, they just kind of cut the average, and they'll show it in the middle, exactly opposite of way down here than the partially negative side. Well, that has consequences, and those consequences are these positives and negatives can attract other things that are positive and negative, or they can repel whatever the like charges are. So therefore, it is of consequence, and it is because water is polar covalent that water has some very interesting and unique properties. Let's move on. Hydrogen bonds, one of the aspects of water being a polar covalent molecule, meaning it has charged areas on it because of unequal sharings of electrons, is that it is able to engage in hydrogen bonding, which is a very strong, what is called an meaning between, molecules, between the molecules. It's an intermolecular force. In the previous presentation, we call this a van der Waals. That's an A. That's a really bad looking A. Van der Waals force. So it's an intermolecular force. And the hydrogen bonding of the three, there's hydrogen bonding, there is what are called dipole forces, and then there is what are called dispersion forces. And hydrogen bonding is the strongest, and that's really what you want to pull out of this conversation. The hydrogen bonding is the strongest. It is a very weak, somewhat temporary bonding, and it is weaker than ionic, it is weaker than covalent. It is simply just one of the weak bonding forces. But of these three that are very weak, hydrogen bonding is the strongest. And it has to do on my diagram over here. Let me again change the color. On my diagram, it is this hydrogen to oxygen between two molecules. If this is molecule 1 and that's molecule 2, see, this is between the molecules. It's not within a molecule, so that's different than what we were just talking about on the previous slide. It is this temporary attraction of the positive side of a hydrogen to the negative side of this other oxygen that allows for the creation of a hydrogen bond, and that's what that is. And we see this in 4 cases on this particular diagram. Here's number 2, there's number 3, and there's number 4. So what do these forces do? Well, this type of bond explains why it takes so much energy to melt water, when normally it should not, by the math, take that much energy, or to boil water. The stronger these hydrogen bonds are, the more hydrogen bonds there are, the more energy is needed to disrupt these bonds in order to actually make something happen, either physically or chemically. Continuing with hydrogen bonds, what do hydrogen bonds do? Well, up here, hydrogen bonds affect the properties of water. Like what properties? Well, like these properties. Cohesion. Cohesion is where water molecules will stick to each other, and that's a very good diagram over here where we see these hydrogen bonds. This is water sticking to water, water molecules sticking to water molecules. This creates something we call surface tension. Surface tension is basically almost like a force at the top of the water that creates almost like a skin on water. It's not really a skin, it's just water. It's not like when gravy has been sitting on your plate for a while and it kind of gets hard on top. That's not like this. But that surface tension actually is just a kind of a force that creates almost like a barrier to like on the top of a drop of water to getting inside the water drop, for instance. And this allows for things like bugs, water skippers, to actually walk on the surface of water. It gives water droplets their spherical shape because all the forces are actually pulling into the center. And so water ends up being spherical. Other properties are adhesion. Adhesion. If cohesion is water sticking to itself, adhesion is water molecules sticking to other substances. Think about the fact that when you drink a glass of water, so you pour some water in a glass, you drink it, and then you pour the rest of the water out into the sink. Then look inside the glass that had the water in it. Is it immediately perfectly dry? Of course it's not. There are little droplets of water still in that glass. No matter how much you shake it, that those water droplets are just kind of sticking to the glass. Water molecules do this because of the property of adhesion, and it's because of its polar covalent properties. Now, an important biological property to water is that it can also engage in capillary action because of adhesion. So this is an aspect of adhesion where water molecules can stick to something, like maybe so that's a really horrible diagram of anything that I would like to show you. Imagine a vein in a tree with kind of hollow areas inside cells. I think it's the phloem or the xylem. And water molecules can actually stick to the surface inside here, and they basically kind of stick and rise up, and that's called capillary action. What this has the effect of is allowing water to work its way up from the roots into stems and leaves. Without capillary action, there would have to be another mechanism to get water up into the plant, and if there was not a mechanism, then the plant could not grow and thrive. All plants would die pretty much right out of the seed or right from sprouting. Let's move on. So here's a really cool photograph, and this is a classic experiment. You may have done this in middle school. Right here, this is a penny, just a 1-cent penny. And what you do is you take a water dropper. There's your bulb, water in it. Squeeze the bulb, and then water drops out. And it drops onto the penny. And the question in science is, how many water drops can you actually put on the penny before the water overflows the penny? And, you know, it's a guessing game. I'll guess, 2, I'll guess 22, I'll guess 117, I'll guess 1, whatever the guess is. And then you do it. Classic experiment. You have a hypothesis, then you test it. And then you find out, oh, wow, I was able to fit 20 drops on the penny. And when I did, the penny looked like this. Look at this shape, this amazing bubble. And this is all water here. And it's right on top. Now, why? The penny's only this thick, and there's a little lip there, but it's just a small lip. Why isn't the water spilling over? And that's because of cohesion and surface tension. Only because of this. That's an N, that's an S. My pen is, well, it's my handwriting. It's not the pen. I can't blame the tool. And so, how many drops can you fit? It's always surprising, unless you've done the experiment before, exactly how many drops of water you can fit on a penny. And the experiment then goes, well, once you do it once and you guessed 7, and it turns out that you could fit 25, then you guess again. You come up with a new hypothesis. This is all scientific method material. And so you would say, oh, well, I think it's going to be 25. And then you find out you get 26. And so then you guess one more time, and you guess 26, and you find that, wow, you can fit 25 or 26 or something like that. And it's just about refining your hypothesis based on experimental evidence using this particular experiment, which takes advantage of water and its ability to have surface tension and cohesion. But of course, it's about scientific method in that experiment. However, I like the diagram because it really gives an example very clearly of water and its surface tension. So here is another example of water and surface tension. That's just a glass of water, and with a very careful touch, you can get a paper clip, which is made of metal, to float on the top of water. Only possible because of surface tension, and you can see all around in here the depression that the metal is making without breaking the surface, because water surface tension is so strong that it can actually, almost like a trampoline, hold this metal up. Now, with a little bit of push, you can certainly get that. You can break the surface tension because we are so much stronger than these bonds. And then that paper clip, because it is metal, will sink like a piece of metal should sink. Now, we've all, if you've ever spent any time out on a pond or near a slow-moving creek, that you see water skippers, these water bugs that can take advantage of the surface tension of water because they are so light, and when they push down on water, water can actually support them. You see the depression of where they're actually stepping right here, and they don't break the surface. They can just walk along the surface, and not all bugs can do that, but these bugs can. However, if you were to break up the surface tension, and you can do this actually by introducing soap. Soap actually breaks up water's surface tension. It just breaks it. If it breaks it, these bugs, like any bug, would literally sink to the bottom like a rock, really. And of course, that would kill the bug because the bug cannot breathe underwater, and so you don't want to do this because it would be inhumane even to an insect. But that would be, that would be something. If you go back and you have that paper clip and you put soap in that water, that paper clip will not float no matter what you do because you've broken up the surface tension. Here is an interesting thing where you drop some water down into some water, and it basically rebounds up and pulls up, and you get a drop out of here. Notice the spherical shape here, again, because of surface tension. Otherwise, it would not be spherical, even down here, and you can see it a little bit down in here as well. Let's move on. Solutions. Okay, so we can take water and we can mix other chemicals with water that will dissolve in water, and we can make solutions. Of course, in chemistry, we use a lot of solutions when we do labs. We were actually getting ready to do a lab. Unfortunately, we missed out on that this year. You'll get to see it in chemistry if you come back around, because it's a lab that I do in both classes, because it's a good lab. And that's where you actually use solutions and you would do a chemical reaction. So substances dissolved in water are called solutions. Solutions are homogeneous mixtures. This water is the solvent, and the word solvent down here, let me underline it. So the word solvent down here is whatever does the dissolving. So water dissolves things. Things don't, water doesn't get dissolved by anything. Water actually does the dissolving. So we call that always the solvent. Anything that gets dissolved is the solute. So think about in sweet tea or salt water. Salt water, you get salt dissolving. In sweet tea, maybe sugar, maybe lemon, certainly the tea that actually makes the flavor for the tea. You can have a compound called copper chloride, which is a kind of chemical salt. Acids will oftentimes dissolve in water, and a compound called baking soda dissolves in water as well. And sometimes when you do that, and then you can add a little vinegar to it and it fizzes. Suspensions. We've talked about suspensions before. There are many, many substances that will not dissolve in water, although water is incredible at what it can dissolve. In fact, it's sometimes almost, and in fact, it's actually called the greatest solvent in the world. However, it doesn't dissolve everything. So a suspension is simply a heterogeneous mixture that you can temporarily mix, but if you leave it alone, it's going to settle upon standing. Consider this diagram here. What we have simply is we have water and we have oil. You can shake it up and get it to mix a little bit, but you see all of the oil droplets. They haven't really blended with the water at all. They simply are suspended through the water. You leave it alone for a little bit, and the oil, because of its density, will float to the top, and the water will stay down at the bottom. What happens? Well, oil and water will do this. Italian salad dressing, which is simply a variation of oil and water. A mud puddle will do this, and blood with blood cells actually can be made to do that as well. Acids. Let's talk quickly about acids. Acids form what are called hydrogen ions, sometimes called, if you have the right textbook, they actually call them hydronium ions. So let's say hydronium. Really, though, I think most of the time your book just calls them hydrogen ions, but if you ever run into this word hydronium or this weird water formula where instead of H2O it's H3O plus, well, think about if you take H2O and you add a positive hydrogen, what do you get? You get H3O, so now you have three hydrogens, and that positive charge comes through. So that's where that comes from. If you run into it, websites, textbooks, things like that, it's just the same thing as a hydrogen ion for us. So acids form these hydrogen ions in solution, which that's what makes them acidic. The more hydrogen ions in an acid, the more dangerous, the more reactive the acid is. And so that's what that says. Stomach acid, which is really hydrochloric acid in your stomach and in mine, which helps to digest food, is a really strong acid actually. But the membrane and the mucus lining in your stomach actually protect the rest of your body from the HCl, from the hydrochloric acid. However, if you rupture your stomach or you get a thinning of the lining, I think they call that an ulcer, and then that acid can actually get out and interact with other organs and then make you sick. Now, how do we measure acid for chemicals? Well, we use what is called the pH scale. pH, the power of hydrogen, if you will, so pH, power of hydrogen, that's why H is actually capitalized, is a scale simply to measure how acidic something is, or the opposite, how basic something is. Because basically what you have is you have acid, then you have neutral, and then you have base. Base is exactly opposite of an acid. Acid is the opposite of a base. Neutral is just in the middle where it's not one or the other. Now the pH scale is a numerical scale, and it runs 0 to 14. Anything below 7 we consider acidic, and the closer you are to 0, the more acidic you are. Like stomach acid is like a 1. So it's almost 0. Battery acid is a 0, like a car battery with battery acid, it's a 0. So Anything below 7 is acidic. Anything close to 0 is very acidic. And how does pH work? Well, it's a numerical scale, 0, 1, 2, 3, 4, 5, 6, all the way to 14. And if you go from 3 to 4 or 4 back to 3, what happens is it's a 10 times difference in the number of hydrogen ions. Basically how these variables work, or these numbers work. We encountered something like this when we talked about the Richter scale, because when you go on the Richter scale for earthquakes, if you go up 1 on the Richter scale, it's not just 1 time more, it's actually like 32 times more energy has just been released. So in this case, when you go between a 3 and a 4, it's going to be a factor of 10 different. So if you had 100 hydrogen ions in one case and you go up or down, then you could have 1,000 hydrogen ions or 10 hydrogen ions. And that would be a 10 times difference. So in 10, 10, 10, right? Okay, well, let's move on. Here is just one of hundreds, probably of thousands of scales that you can pull off of the internet that show you the pH scale and a few things about the pH scale. This one happens to actually be in comparison using, let me see, I have a pen here, so let me go ahead and activate the pen. Here you go. Basically comparing pH values, and it is concerning aquatic life. So, all right, well, way down here, this is 0. So this is like battery acid, lemon juice, vinegar, tomatoes, which are very acidic. Carrots have some acid in them. Normal rain is actually acid rain. It's acidic because of the carbon dioxide, and acid rain is becoming more prevalent as we have more carbon dioxide in the air. Even milk is slightly acidic. So with all of these things, in aquatic life, if you get down here between 4 and 3, you kill fish. Between 4 and 5, the things that fish eat start to die, so they start to lose their food source, even though the fish may be able to live in that area. It kills the larvae that rely on the water, that are actually in the water. Between 5 and 6, you get salmon eggs and alevine dying. At 6, just slightly under 6, around 6, bass and trout begin to die because they are very sensitive to changes in acid. If you have a pH between 6 and, I guess it looks like 6.5 really, snails and tadpoles, so now you're going to kill your frogs and your toads and snails. So fish actually operate when it's slightly over neutral, a little bit basic. A little bit basic, it's going to be great for fish. However, too much of a good thing is too much. So you get up here to about 9.5, you kill your fish again. So if you want to run a fishery, if you're going to work in a fishery, here is your sweet spot right in there. And that's where you're going to test your water probably daily. There's probably an automated way to test that water every time because, of course, fish are your product and you're going to be selling those fish. And so therefore you're going to test the water and make sure that not only all the chemicals are right, but the acidity is right, which by the way is the same acidity level or base level as human blood. No surprise there that things tied to the water and humans are also tied together, which is one of the indicators where all life, including what led to people, began in water. So just evidence for it. Okay, pure water. Pure water is neither acidic nor is it basic because it has a pH exactly 7. And if you consider a number line that goes from 0 all the way to 14, on a number line, 7 is literally in the exact middle. It's not closer to the high side, it's not closer to the low side, it is dead on in the middle. And so therefore, we say that is neutral. And so just as far as pH, it's neutral, and pure water is neutral. Now your tap water and mine, not neutral, and I don't care if it comes out of a well or if it comes from the city. That there are a lot of chemicals that will either be naturally dissolved in well water or there will be added to processed water from like a city water plant. And that is for health, killing bacteria and things along those lines. So pure water, 7. Drinking water, probably not 7. Remember, the 7's in the exact middle, And it simply indicates that the things that make an acid acid, which are the hydrogen ions, are equal to what makes bases bases, and that's called a hydroxide ion. So a hydrogen ion, the more you have of these, you have acid. The more hydroxides you have, the more base you have. And if you have equal numbers, then you have pH of 7. Bases. Bases are called alkaline solutions when they are dissolved in water, and they would have a bitter taste. If you've ever gotten soap in your mouth when you're in the shower, in the tub, or something like that, or unfortunately, if you, like me, may have experimented with colorful metaphors, swearing words when you were younger, and your parents may not have appreciated you swearing, that you may have had your mouth washed out with soap. I know I certainly did many times. I will say that I'm okay with Irish Spring, but Ivory soap, blah, leaves a bad aftertaste. In any case, it's bitter tasting. Soap is bitter tasting. Why? Because soaps have bases in them. Oops, not based, bases. Thinking of having horrible nightmares, reliving that soap issue, right? So anyway, bases form hydroxide. These are, remember, called hydroxide ions in solution, and that's what makes them bases. The more hydroxides you have, the higher you will get to 14 on the pH scale. This means more hydroxides. Hey Spence, can I write it HO? Nope, you can't do that. That's what Santa's like patented that when he's copyrighted that. We're not allowed to use it. So we use OH, just to make sure that you're aware, and the OHs have a negative charge to them. So a basic solution will always have a pH reading above 7. And that above 7 simply means now you have more hydroxides than hydrogens, therefore it's going to be more like a base. And the closer you get to 14, the more hydroxides you have, the fewer the hydrogen ions you have, and the more basic it is. And that term is typically, they don't say corrosive, but they say caustic. It's just a different type of reaction, but to you and me, it would be very harmful on your skin if you ingested it, things like that. So real harmful. So a pH over 10 indicates you're getting towards stronger bases, which become more and more dangerous. Lye soap, which is actually used, you have to be careful using lye soap, and specifically this thing called oven cleaner, like there's one called Easy Off, and there are a couple of other products out there. But these oven cleaners have a pH of around 13. That makes these very dangerous. I actually burned myself. I was just not paying attention. I was cleaning a stove, and I had to clean it several times in an apartment that was being rented, and the stove had to be cleaned, and so I had to hit it with a lot of oven cleaner multiple times. So many times that I got careless. And I got some of it on my arm, didn't know it at the time. I was just cleaning and cleaning, and all of a sudden my arm started burning. And so I just itched it, scratched it, whatever. And eventually I looked down and realized that I had gotten oven cleaner on my arm, and I actually had a chemical burn from it. It's just really, impressive, because I never really thought about it. And I knew, because I'm a chemist, I should have known, and I just got careless. Buffers. And this is specifically for certainly organisms. Organisms are not prone to big changes in pH in their environment, like fish. A little bit one way or the other, and your fish are going to start dying. Their food sources start dying. So there's kind of a sweet spot there. So all organisms inside themselves, for that homeostasis we talked about, also have to be able to regulate acid-base stuff, and that's called buffering. So in this case, let's check this first bullet out. The pH of body fluids, and we'll just stick with humans here, in human cells is normally kept between a 6.5 and a 7.5, just hovering right around neutral, but not quite neutral. Little acidic, a little basic. So, either way, there's a short range there where our systems will work just fine if the acid level is anywhere in between there. If, however, the pH changes too much, if it drops below 6.5 and becomes more acidic, if it increases over 7.5, again, it's not a good thing either. If it's a little too basic, too many hydroxides, which are reactive and start making products and changing things in bodies that we don't want. If the pH changes too much, functions can be impaired, homeostasis cannot be maintained. So our bodies are filled with buffers. buffers are actually weak acids or weak bases, and they are contained within body fluids, and they help counter drastic changes in pH. They're able to absorb some of the extra hydrogens. They're able to absorb some of the extra hydroxides. And by that reason, they are able to resist that change of acidity because they are removing some of the acid or some of the base as the acid and base are introduced into a human system, for instance. So these buffers help to maintain a pH balance in cells. They help to minimize changes in pH, and our blood contains wonderful buffers to help all that out. Because think about blood. It goes everywhere in the human body. There's not a place in the human body you can't find blood somehow, somewhere. And I know because I've gotten cut in the weirdest places, just way out, like behind your ear, you get a scratch or something like that. I've ran into a nail before that was sticking out of a door. And, no matter where you get scratched, you bleed. And I mean, no matter where you get scratched, you bleed. And so that tells me blood is everywhere, but blood actually is helpful because it contains buffers, as well as, of course, the primary reason for blood to exist is to carry O2 to your cells and to carry carbon dioxide away from your cells, which is cells need O2. Carbon dioxide is a waste gas, which is poisonous to cells, and it carries that away back to the lungs where we exhale it out into the air. Here are some magnified pictures of red blood cells. They look to me like little bowls, actually. So that's a healthy blood cell. And I believe it's actually in these depressions is where the oxygen actually bonds, just as far as the bonding site. Now, these things, we are looking at billions of atoms in this little magnified image that make up one red blood cell. Maybe not billions, maybe trillions. So billions times billions, maybe. But in any case, so we wouldn't see the oxygen if it were in there or not. But this is where I believe the oxygen actually bonds. And then red blood cells carried through the liquids in blood, the plasma, are able to then move throughout all of the veins and arteries even, and capillaries. Okay, so this slide tells me we are 2 slides away from being done today, or being done with this presentation. This, of course, being the key learning again and the unit essential question. This takes us over to section 2.3 on carbon compounds. And this next presentation, which would actually be part 4, which will cover section 3, I believe will cover both sections. So section 3 and 4, section 3 being carbon compounds and section 4 actually being about chemical reactions and enzymes, which are really an extension of carbon compounds anyway. So we're going to throw all of that together, I believe, into one presentation, unless it gets too long. If it does, I will actually break it up into 2 parts. Otherwise, there we go. I will see you in the next presentation. Hopefully you took all your guided notes, because that's what you should be doing. And when we're all done with the presentation, all done with the guided notes, then go and fill out that Chapter 2 all section worksheet. One worksheet, all sections, and I think 50 questions. So there you have it. Thank you.